In this ProteusDS training session, we're going to go through detailed mooring design with ProteusDS Oceanographic. What we're going to cover is working with Oceanographic Designer, working with parts libraries, assemblies, and adjusting the design. One of the sample mooring files you can download and play with is Datawell 200 meter water depth mooring. You can see there's already an established set of components like shackles and line lengths and things like that. Now you can start with one of those ones and make adjustments, but you can always start with your own mooring from scratch as well. And it's not really hard to do to get started with a lot of fundamental components. You can see I've downloaded the official parts library already, and you can see that there's several sample mooring files here, including the Datawell 200 meter mooring and the official parts library. When you open the official parts library, you see there's a ton of existing components from organizations like Deepwater Buoyancy, mooring systems as well, lots of different ADCP sizes, wire rope options as well, lots of different flotation options as well. So to get started with ProteusDS Oceanographic Designer, you do have to add the official parts library as a first step. You can make your own project parts library files and add them as well. The first thing we're going to do is add some wire rope. So you pick line, and we can pick from the options we already have here. So 3x19 1/4 inch wire rope. You can look at read-only properties of the components there. Let's say we're picking 500 meters wire rope length. The default water depth is 100. You can change that under the environment settings as well. Okay, now we're going to add an assembly with a subsurface buoy. So we'll call this assembly top float. There's nothing in it right now. So we go over to the subassembly window and click on the plus. Let's pick subsurface buoy, Deepwater Buoyancy, and say a 750 meter depth rate, a 36-inch sphere. And you can see the dry mass is adding up, and this is the wet weight. Negative means it's flotation. We're getting changes to the aggregate total dry weight and total wet weight of the mooring as well, and the aggregate length. If we want to add an instrument to this, click on the puzzle piece, and then we can start playing with attachments. So for example, we could pick a Teledyne Long Ranger ADCP. You can see 86 kilograms and a wet weight of 55 kilograms. It's kind of adds a lot of weight and takes away from the flotation capacity. Now you notice this parameter, flow opacity. What does that mean? It's a percentage of how much flow is essentially blocked, so it gives an idea of how much drag there is on that component. It affects the drag calculations. Most of the time, if you have a single ADCP layout, only a small bit of the ADCP will be poking out. So oftentimes, if there's just one ADCP, I might say 10% flow opacity. But if you have a dual configuration, the other ADCP may be sticking way out on the other side. So if it's dual configuration, I might choose something closer to 100%. So let's go back here, and I'm going to change this to about 10%. And go OK. When you're adjusting the design, keep an eye on the estimated depth, because that's going to play into your target instrument depth for the project. So approximate depth at top of the component. This is factoring the stretch of the components as well. This is where we might adjust the wire rope length if we were trying to target a different depth for this. I'm just going to leave this for now, but this is the number to keep an eye on when you're tweaking your mooring configuration. Other things you can do, and I recommend typically making frames in a project parts library. When you add a frame, maybe the default value you'll see is for flow opacity is 10%. That's not a bad number to start with for the frame. But as you add instruments to the frames, typically I'd leave the flow opacity at 100% for all of them. And then it's just calculating the drag from all the components. Here's some example frames from Cyro and IMOS. I believe these were used in the EAC moorings, but it might have been the SOFS moorings as well, both of which are available in the sample downloads. When you're working with acoustic release assemblies, for a dual configuration, we usually will create a specific parts library component for that. And you may see some of those already in the official parts library. So under acoustic release, you'll see under, just for example, XS, there's a single acoustic release. The total mass is 36 kilograms. The length is 94.6 centimeters. And then when it's dualed, it's just multiplying those by 2, but the overall length doesn't change. Here's a picture of an anchor assembly. Thanks again to Cyro and IMOS for the picture. There's several railway wheels set up in this assembly. The best thing to do for these is keep it simple and be aware that in the parts library, you're just trying to get the general size set up correctly. Mass and wet weight can be set based on the material of the anchor. It's optional because in the dynamic and static analysis that we'll be doing in the future, we pin the anchor in place. However, if you really want to do a deployment analysis where you're seeing how the mooring is going to fall through the water, you do need to have an anchor on in your design file. Profilers are an interesting facet of working with mooring design because they can move up and down. Here's two examples from Delmar Oceanographic and McLean Research. There's a couple ways to do this today. The simple way is to make an instrument. Remember, there's instrument types and a bunch of already filled out examples. The wet weight of them of these units, they're typically pretty close to neutrally buoyant. So the wet weight you should place somewhere around, a little bit heavy or a little bit a little bit positively buoyant or a little bit negatively buoyant. The mass should be the total aggregate of all the stuff that you've added into the system. The more detailed hard way is you can make a frame and then again set the wet weight to something slightly negatively buoyant or something slightly positively buoyant, and then make sure you have the frame mass, and then you can add attachments to the system. And it'll kind of account for the mass of those components. So the frame of an empty, for example, wire walker is not going to be as heavy as when all the instruments and ballast and everything's added into it. And with a profiler, typically the ideal situation you want to do is make sure you start with a profiler in a place where it's kind of maximizing the load on the mooring. That might mean it's kind of in its higher position on the system. That way it's going to create the highest drag loading on the system if the current profile is largest near the top of the mooring as well. And there'll be some exposure to wave loading from if it's closer to the surface as well. But you can always make sensitivity cases to investigate what happens in the dynamics, but that's for future training presentation. Don't forget about the bill of materials export up here and the assembly layout. gives you the order to assemble the components in. It'll look something like this at the moment and give you a list of all the components of each kind in the system. In mooring diagram view, you get an automatically generated schematic of what the system looks like. Our system so far is really basic, so there's not a lot of details to look at. But it's a good way to automatically get started in looking at what the mooring visually looks like. Generally, with some good practices are use a standard approach with connectors, assemblies, and take advantage of the duplicate function. So if we go back here, often what I'll do is make an assembly, and we'll call it connector assembly A. We might look at a combination of a safety anchor shackle, 5/8 sling link, and then another safety anchor shackle on the other side. So I'll just move that down there. Great. Shackle, sling link, and shackle. That's connector assembly A. And we can use this duplicate function over here and then move it down here. So we've got one between the wire and the anchor. In terms of modular mooring design, in surface moorings, it's really handy to have these segments of wire that you can adjust and help configure where the estimated depth of the instruments are. So there's several ADCPs in frames on this mooring here, and then these segments of wire rope are often what gets adjusted to fine-tune the position of these moorings. And then when you want to adapt the mooring for different water depths, then you've got this compliance section down here, which is the area that you could really configure and adjust for that water depth. So modular mooring design is a really great way to make it easy to adjust where the sensors are. This is taken from a detailed drawing from the SOFS mooring by Cyro. So in review, we covered looking at Oceanographic Designer, working with parts libraries, assemblies, and making adjustments to the design in the detailed design phase. Thanks for watching.